Hello. This lab will be looking at magnetic braking with Faraday. The purpose of this lab was to measure the time a magnet takes to fall out when dropped through a tinfoil tube and then compare that time to a computational model we made using Faraday's law. The results of this lab was that it takes an average of 0.885 seconds in the real life for the magnet to drop through the tube, while the computational model calculated the time to be 0.823 seconds. We'll start by going over the fundamental physics principles, assumptions, and initial conditions we need to know for this lab. Then we'll compare our observed results to the model made through GlowScript, and finally we'll conclude with a brief discussion. The first fundamental concept we need to know is Faraday's law, which is seen here. And using this law, we can use the change in magnetic flux to predict the current induced on the tube. Next, we have Biot-Savart law, which we can use to find the magnetic field that the bar magnet exerts on the foil tube, and also calculate the magnetic force on the tin foil. Finally, using Newton's second law, we can make a velocity time graph of the magnet and use Newton's third law to make assumptions about the force the tin foil exerts on the magnet from action-reaction forces. These are some initial conditions we need to know to make the computational model, and note here that the magnitude of the magnetic dipole moment, mu, 2.43 ampere square meters, that was found from lab 3. And overall, through 5 trials, the average time it took for the magnet to fall through the tube was 0.885 seconds. Now, after we plug in our initial conditions into the GlowScript code, we set up a function that calculates the magnetic field of the dipole using Biot-Savart law. And then we have a function that calculates magnetic flux that gives us df dt. And then in order to calculate the force on the magnet by the tinfoil, we first calculate induced current using Ohm's law in step 4, and then also the magnetic force on each ring of the tinfoil. Here we calculate gravitational force and magnetic force. Combined, that gives us net force. And then in step 8, we are updating the magnet's velocity and position. Here we have a snapshot of the visual model. If you want to see the rest of the animation, please click the link in the description box below. And then here we have the velocity versus time graph. We found that it takes 0.823 seconds for the magnet to go through the tube, and this is according to the computations. And note that this is pretty close to the observed time that we got. And we also see in the graph here that while the magnet falls in the actual tube, it has no acceleration, which means that there's no net forces acting on it, which is pretty cool. So what if the resistivity of the conductor was reduced close to 0? This would mean that the current induced on the metal would be higher. Therefore, if we use this larger value of the current induced to calculate the force would also be larger. Therefore, the magnet would take longer to fall. And then, what if there were holes or slots cut into the tinfoil tube? In this case, the induced current would be lower, which means that there would be a reduced magnetic force. Therefore, it would take a shorter time for the magnet to fall, which means it would fall quicker. And that's all for this lab. Thank you for listening.